So I guess we can start. I'm Ricardo Rocha from CERN. I'll be presenting our work with multi-cloud federated Kubernetes at CERN. This was some work that we've done together with Kleinimar. He couldn't make it to the summit, unfortunately. So I'll talk about what was also demoed early in the day at the keynote. I'll go through it a bit in more detail, and then I'll try to give the demo again. And it made it the first time with a hic, so maybe I'm pushing a bit, but we'll try again. So a bit about CERN. So CERN is the European Organization for Nuclear Research. It was founded in 1954. And its main goal is fundamental science. So we try to answer some big questions like what is 96% of the universe made of? We only see 4%. We know the rest is there, but we don't really know what is made of. What was the state of matter just after the Big Bang? Something that is called the quark-gluon plasma. So we have dedicated experiments to investigate this. And why don't we see any antimatter in the universe? We know that in theory, both matter and antimatter were created in the same amounts, but for some reason we don't see antimatter. So this is something we are researching. So this is a picture of the Large Hadron Collider, which is our main accelerator right now. It's 27-kilometer ring where we accelerate protons in 2 directions. And we accelerate them to close to the speed of light. And once we get them in a stable flow, we make them collide at very precise points. So we achieve this kind of energy and speed by using superconducting magnets. So inside the accelerator, it runs at very low temperature, very close to the absolute zero, something like minus 271 degrees. So you can also go to the tunnel when it's not operating, and you can take your bike and go around. We use it to do repairs and things like this. So right now it's operating, so the access is quite restricted. But if you pass by CERN in a moment where it's not operating, I encourage you to go for a visit. We organize them often. So this is the view of the CMS detector. It's called a compact muon solenoid. It's 14,000 tons, so it's a big thing. It's 26 meters wide. And it's actually, as it is also the accelerator, 100 meters underground in a big cavern. So you can see the person there to give an idea of the size. And this is where we do the collisions. So once we have the stable beams, we make them collide at the center of these detectors. We have 4 of them. And then all these electronics are used to track energy and the flow of the particles. So that we can see what's going on. In practice, it's a big camera. Just because of the high energies, we have to use these kind of machines to observe what's going on. So why do we have such computing needs when we have all this effort to do an analysis? These collisions happen at very high rate. We can have something like 1 billion collisions per second when the detector is operating, or when the accelerator is operating, which generates a large amount of data, something like a petabyte a second, that we can't manage. We don't have not even close to the computing capacity to process this kind of data. So what we do is we have filters very close to the detectors where we do the early filtering of the data. So we have some based on hardware and then some based on software. And with these filters, we can reduce the data being generated from 1 petabyte to something like a couple of gigabytes a second, which we can manage. And we store this, we call it raw data. We store it on tape in our data center for archival. And with this, we generate something like 70 petabytes of data every year. So it's still quite a lot of data, and we need a lot of computing capacity to handle this. So this is a view of the resources we have in our cloud. You can see on the top left something like 320,000 cores. So it's quite a lot. We run 37,000 VMs. We have quite a lot of users and projects. For this talk, it's important what's there as Magnum clusters, which are container clusters. They are mostly Kubernetes clusters. So we have 210 Kubernetes clusters that run different workloads from things like batch workloads and analysis that I will discuss today, but also CI/CD Spark analysis, and many other things. People can just create their clusters and do whatever they want with them. Now, even with this kind of capacity that we have inside CERN, we still don't have enough capacity to process all of this data. So over the years, we've developed a distributed computing infrastructure that has 200 sites distributed around the world. We connected them together, and CERN is the source where the data is stored initially. And then we push the data to these big tier 1 sites, some 10 to 12, which are also quite big, and where we do the first step of reconstruction to see what we had in the data. And then we have a bunch of other smaller sites that we call tier 2s, where we do additional steps of analysis of the data. So in total, we have more than 200 sites. At any moment, we'll see something like 400,000 jobs running at the same time, and in total, 700,000 cores. So it's a large infrastructure. What it also means is that we have a lot of experience running distributed infrastructures, and so we relate it immediately to things like the federation functionality in Kubernetes. So here's some motivation for the federation work we've been doing. The main one, one of the main ones is periodic load spikes. We have a lot of capacity in-house, but it's mostly used all the time, which means that when there's spikes on the load, on the requests, something like in the summer, there's a lot of big physics international conferences, and people just jump and try to do their analysis just the weeks before, which means we need to provide more resources. Also, the experiments often change the calibration of their detectors, and they do some reconstruction of the data they had already collected, and they also need these extra resources at these times. Also, a lot of simplification. We have custom tools to monitor the different applications. When we started using Kubernetes, then we get a common layer to deploy the applications, but also to do the monitoring and even the alarming. So everything is integrated in the same definition of resources and the same APIs. This simplifies our life quite a lot. So that's what I mean by deployment. Uniform API means that no matter what the specifics of the application, you will deploy it the same way. It has integrated functionality to the replication if you need to increase the number of replicas of your application, and does load balancing internally and also external load balancing. So these are all things that simplify a lot our lives, and so that's why we started looking at federation. In-house, we've been using containers for a couple of years now. So in early 2016, we started looking at OpenStack Magnum as a way to deploy container clusters. And in the end of 2016, we made the service into production. And since then, it's been growing quite a lot, the usage. So in summary, Magnum, what it offers is a way to deploy container clusters. It's a container engine agnostic, so it supports Kubernetes, Docker Swarm, Mesos, and DCOS. It allows you to do this by using your OpenStack Keystone credentials, which is good because we already have a lot of services relying on them. It supports multi-tenancy in the sense that the clusters are deployed in your own project. And then you can also have things like multi-master and integration with some load balancing service if you're running things like Octavia. So it's very well integrated in OpenStack, and it provides the functionality we needed, which is very similar to what you get when you go to the Google Cloud Platform and you create a Kubernetes cluster, which is like one click and you get a cluster. So very similar functionality. It looks like this. So to create a cluster, there's one command. You do COE cluster create. You specify the kind of cluster by providing a template. In this case, I provided Kubernetes. Yeah, and then the size of the cluster, in this case 100, and then a name. We've done tests. Most of our clusters are tens or a couple hundred nodes. We've done tests with clusters up to 1,000 nodes. And we had good results deploying such clusters, and we've done also some performance testing on it. So it takes a couple of minutes to create a cluster. And then once you have it, you just have one command to get the authentication credentials so that you can talk back to the cluster. Once you do that, one main feature is that you use Magnum to orchestrate the deployment and to manage the cluster, but actually to access the cluster, you use the native APIs. This is a main point. It's the same. If you would use Kubernetes, you will use the kubectl command. If you use Docker Swarm, you just use the Docker client. So you just access directly using the native APIs. It provides other kind of functionality once you have the cluster, like expanding the cluster. If you want to grow it, in this case, we would increase the cluster size to 200. On the other side of the picture of what we will talk here today is Kubernetes. So just a quick summary of what Kubernetes is. We don't have time to go into detail, but basically it has a control plane that is the Kubernetes master, where you have the API used for the interaction with the service. You have the controller manager that will manage the different kind of resources that you can create. And you have a scheduler that will do the assignment between whatever resources you're asking to create and the availability in the nodes. Then on the other side, you have the minions or workers, where you run for each one a kubelet, which is the daemon that will manage the local containers, and the kube proxy for the load balancing and the access from the services. So this is in summary how it looks, the architecture, and then the main thing here is that you can deploy multiple kinds of resources. So the typical ones are pod, service, deployment, daemon set, but there are many others. So a pod is basically like a container, but you can actually have multiple ones sharing the same file system and the same network. Service is an access point, an endpoint that can have multiple replicas behind it. It will load balance between the different replicas of your service. A deployment is a collection of these kind of things that you can deploy as a single unit and scale in one go. A daemon set is something that we'll talk about here, which is when you want to run the same container in every single node. Like if you have a system container that you need for certificate handling or some kind of authorization that you want to run on every single node. And jobs are an abstraction which correspond to pods in reality in the deployment, but that allow you to do things like the traditional batch schedulers. They have a lot of others, like stateful sets for running databases and similar things, but you can also do advanced things like define limits on what your pod can use, both in capabilities and in the kind of resources you can use, how much CPU, how much memory. You can define retrial policies if you want, for example, if you submit a job and you want to retry until it succeeds. You can do taints and tolerations, which is a very cool way to say, to restrict where your pods can run in your infrastructure. Like if you have specific nodes that advertise capabilities like GPUs, you would be able to advertise that to the scheduler, and it will. And then when you define your pods or your deployments, you will say this can only run when the node has GPUs. So on the right side, I put an example of what a job looks like. The reason is because that's the use case we'll be using. So you can just say it's a YAML manifest. You do the same for any kind of Kubernetes resource. So it's not very complicated, but quite powerful, though it's defined. So this was an overview of the technologies we used for these use cases. Now I'll go into detail into two of the use cases we've been looking at. The first one is it's a legacy application that we use, but it's actually our main application. So out of the 320,000 cores we have, something like 90% of them are used for our batch system, which is what is doing all the crunching of the data we collect. So we use a tool called Condor, and this is the first one that we looked at because it looked like it was a good candidate to deploy with it, and also where we could benefit more if we managed to federate it. So here's an overview of how this tool looks like. So it has a couple of components. On the left side, we have what's called the sked, and the sked is just taking requests from the clients. So the requests are defined using class adds, which is this language here, which looks very much like key value pairs. And so here we are defining a request that says that the accounting group is Atlas, the priority of the job, I will need 2 CPUs and this much memory. On the right side, we have what the resources themselves advertised, and they use, in the nodes themselves, there's a daemon running, it's called startd, and the way it advertises its capabilities, it's using the same class add kind of definition. So these are, again, key value pairs. In this case, we say that the environment is production, the data center, so we actually have 2 data centers, so this is specifying which one it is. Other kind of special requirements it might have, in this case, MPI, and the resources, CPUs and memory. So then the collector will just grab all the class adds from both the requests and the nodes, and the negotiator will do the matching between the 2. So this is something that is, it's a system that exists for several decades now, and we have a lot of experience with it, so it was a very good candidate to take and try to containerize so that we could deploy it in a Kubernetes environment. It does have some advanced capabilities that I list here in addition to the matchmaking. It supports fair share and preemption. This is really important for us to be able to have the same cluster being shared by different, in our case, different experiments. So this is something that Kubernetes does not have for now. So in the terms of the requests and the scheduling, it's not something we could do immediately with Kubernetes. We also have a lot of experience with it. We run it mostly virtualized. And from this point of view, when we talk about federation, it's mostly federation of the compute part. We are not talking about federating storage or networking. For this, we rely on a well-established distributed infrastructure that we already have. So we simplified the use case to the federation of the compute, which is where we would gain the most for now. If we look at this picture, the easiest way to do all this work would be to containerize the startd. So this is what we did. We took the startd component, which is the one that runs on the nodes. We made it a container, and we started managing it using Kubernetes. What we gained from this is that deploying this on all the VMs we have, it means that we also have to deploy the monitoring tools, the log collection. If we start deploying in Kubernetes, then Kubernetes gives us all of this for free. So this is a big plus. It also manages the lifecycle of the daemons on each of the nodes. So if they crash for some reason, it will try to restart them. So this is simplifying our deployment quite a bit. So the actual deployment, a federated deployment of Kubernetes has a host cluster and a bunch of other clusters that connect to this host. So what we did is we deployed a Kubernetes cluster at CERN that has the components we saw from Condor, the sked, negotiator, and collector, which is like the central control plane for this tool. And we created a federation. So to create a federation, all we need to do is one command using the kubefed client that is from upstream Kubernetes, and we do init. We give it a name, and we say which cluster is to be the federation host. What we started doing in the OpenStack community is adding this functionality to Magnum itself, mostly because managing the credentials of the clusters can be kind of tricky. So as Magnum already knows about this, it's quite easy to do this integration and just rely on Magnum to manage the credentials. So this is already being pushed upstream. I'll give some more information after. Then once we have the host of the federation, we can deploy a bunch of other clusters. So at CERN, we actually partitioned the deliveries of the hardware in something like 200 physical hosts usually, which kind of match well the size, like the good size for a Kubernetes cluster that we've experienced with. So we can think of it like for every delivery, we'd create a separate cluster. We add it to the federation, and it's up and running. This works extremely well. what we've seen is that we deploy first the Kubernetes cluster independently, and because we define the start D as a daemon set, once it joins the federation and the federation has the daemon set defined there, the resource, it will just pop up on every single node of the new cluster that we just added. The start D is launched automatic without us having to trigger anything. Connects to the scheduler or to the collector and starts grabbing jobs. So this works very well. So it also allows us to do not only CERN, but we started experimenting with deploying clusters externally. So in this case, I give an example of T-Systems, which is a cloud in Europe also backed by OpenStack. So as I mentioned, the start D itself is defined as a daemon set. This is how it looks. It's actually a very simple deployment, extremely simple, but the benefit is very big. So what we do is we define a container that should run on every node, and we actually give it a lot of privileges because it needs to run the jobs. So we say something like host network true and privilege running as a privileged container. And then we define a liveness probe. So this small definition is giving us the deployment of the start D component. It's giving us the checks for if the daemon is working well or not with the liveness probe. So all of this is just coming with Kubernetes capabilities. We use Helm. So if you use Kubernetes, Helm is kind of the package manager for Kubernetes. It's a very, very good tool. If you look there, if you're interested, if you have some deployment where you already use Condor, we wrote a Helm chart for Condor, and there's the link. Now, one interesting part of this deployment is managing storage. So there's two parts of the storage story for us. One is the physics data, which we have a lot, and we already have a well-established infrastructure for this. So as I mentioned, for that part, we consider it as being external to the federation for now, and we just access using other protocols. Now, for the software, where the jobs will rely on, the algorithms that do the data analysis. For this, we use a file system called CERN VMFS or CVMFS, which is not much more than a bunch of hierarchical squid caches with a Fuse plugin. So the stratum 0 is CERN, where we populate the repositories, and then at each site, we deploy this CVMFS component, which acts as a squid cache, replicating whatever data is being requested, but not more. So if a certain package is requested at the site, it will fetch it and it will cache it locally, but not the whole archive, which is just too big. So this works very well, and we are managing this also with Kubernetes. So in addition to, we started only with the start D, but actually we already deploy also these squid caches at the sites in the same way. So we can imagine that with time, as we get more confident, more experience with Kubernetes and this kind of deployment, we'll be adding more and more functionality of the system to this setup. So a bit about the integration in Magnum. So there's a spec for the federation support. It lists the three main use cases, which kind of what I already mentioned, which is expanding to external resources. There's also, if you have multiple clusters with different capabilities, maybe you want to keep them in different clusters and federate in one endpoint. Another one that is here is if you want to share the existing clusters between a set of users. You can add and remove without disrupting. So the state of this implementation is that the API layer and the persistent layer are already merged upstream. The Kubernetes support is under review. The code is there, but it's currently being reviewed. So it will probably be there already for Rocky. On the other side of, so this is the part of an OpenStack, where we are also collaborating, with the Kubernetes community. We started talking to the multi-cluster special interest group inside Kubernetes, which is where the federation work is being developed. We recently learned, so we based all this implementation on the V1 of federation. They've actually started doing a big change. So they now have what they call Federation V2, which is quite different, more flexible. So V1 is a very simple way of allowing any resource that already exists in Kubernetes to be federated. In V2, there are like independent federation resources definitions, and they have also more components, but it's also more flexible. You can define the resource using a template, and you then can define also overrides for that resource, and you can define placement policies to see in which clusters this job or this application can actually run. So we'll keep working in the Kubernetes community too. So this was the Condor use case. The other use case that we did was once we started getting more experience with managing Kubernetes, and we took our legacy app and learned how to deploy it using Kubernetes. We had a new application that was being developed within one of the experiments mostly by Lucas Heinrich, which is collaborating with us. And it's a pure cloud native application, so it has from the start already definitions of jobs, and it uses all the resources of Kubernetes. In this case, we can explore a lot more the functionality. So this is what I demoed this morning, and I'll try to demo again now, if it's working, which it is. So I'll demo again, and then I'll leave it to questions so that we can go a bit more in detail. I think I just lost my network. Okay, maybe I'm not demoing it. Okay. Now, I have a backup video, which I'll play. Okay, so here we go. So I'll play here. So this actually uses a script. Some people asked me earlier today about, it's here, about how I was doing this quick typing. So this is called demo magic. So in this case, we have the context, as we saw this morning, of the different clusters. So 3 of the clusters are deployed in Magnum using the normal Magnum tools I just described. So here we see the federation command will add to Magnum. And we can see that there's already a federation in Kubernetes. When I get the clusters, there's no cluster yet there. So to start adding the clusters to the federation, we can use an OpenStack command soon, which is COE federation join. For now, we have to use the native Kubernetes tools. So in this case is kubefed. So we add 2 clusters, and we can see now that we have the 2 clusters already in the federation. So the next step is to actually deploy a workload. So we use this Yadage workflow service. So we'll do a Higgs analysis like we did this morning. There's different kinds of analysis in these examples. So let's start with the Higgs. So this is a very large workflow with a lot of jobs, which is good for showing for an example here. Because there's a lot of workloads being deployed. So once the workload is ready, then it will start generating the jobs. So I can actually probably move it quickly forward here. No, it's okay. So a bit of details on how these clusters are managed. So the 3 ones, as I mentioned, are deployed at CERN. So Atlas Recast X, Y, and Z are 3 clusters deployed in the CERN infrastructure. Then we have the T-Systems cluster that is deployed in an European cloud based on OpenStack. And then we added GKE. We actually tried to go even further and add as many clouds as we could in another experiment. So we managed to add also clusters in AWS, clusters in Azure Kubernetes service, in an Oracle cloud, And we had at some point like something like 7 public clouds in the same federation, and they all work in a seamless way because we have this uniform API. Once you have your application defined within Kubernetes, then you can immediately start using it. As long as the cloud you want to use offers a Kubernetes service or an easy way to deploy Kubernetes inside, then it's very, very easy to start running your workloads there. So the workflow generation takes a while, but once it's done, it starts deploying all these jobs in the different clusters. So in this case, you can see the second one from the top is the federation one, and it has a bunch of UIDs, and each job in the federation will have an instance of the same job within. Now here we see the logs that come from the application. This is a very powerful feature of Kubernetes, is that it also does the log collection from the application. As long as your application is putting the output to std out, it will do the log collection for you, so you don't have to do it yourself. So in this case, what we will do is we had 3 more clusters, as I mentioned, so we'll add them to the federation, and eventually we'll start seeing the jobs popping up. So here we do the same kind of command, kubefed join, we pass the recast Z cluster, and then we do the same with T-Systems and the same with GKE. And it takes a couple of seconds for new jobs to be generated, but once they are, then they will show up here quickly. There we go. So we have a couple of jobs running on each of the clouds, of the clusters. So this is a very complex workflow with like a couple tens of jobs. So it takes too long, but you can see that it also reports on the status. So this is the actual Kubernetes job status. You can see the green for jobs that have been successfully completed, and yellow for the ones running, and gray for the ones that are still to be queued. So this means that it takes a while to run. So that's the demo. If I go back to the slides, yeah. Okay, so this is the same demo we saw this morning. I'll just conclude with a summary, and then we can have a couple of questions. So in summary, like from our perspective, federation support in Kubernetes is ready. This was using the V1 API, so there's a lot of work going into V2. So the next step we have is to start evaluating this new implementation of federation. There's also a lot of discussion within the Kubernetes community on how to properly do multi-cluster. There's another option, which is to just expand the service mesh to outside your on-prem or your home cluster to achieve the same functionality. But from our point of view, because we are doing batch jobs mostly, actually federation is a good match. So for other use cases, it might be that if you need to expose service endpoints, it might be that it's not such a good match. OpenStack Magnum is embracing also the federation functionality to ease the management if you're using Magnum to deploy your clusters, to ease the management of the federation. We are using this at CERN. So we started with a legacy application, as I mentioned, which is Condor, with limited integration in the sense that we only containerized part of it, but we expanded it quickly to a cloud-native implementation, and this has been working very well. And mainly, like we really have great support from both OpenStack, Magnum, and the rest of the OpenStack projects, and also in Kubernetes. So it's been very easy and interesting to do this. And I finish here. So I think we have like 5 minutes for questions. Thank you.
Excellent, fantastic presentation. And just to get some understanding of it, this is applicable for high performance computing, is that right?
You mean the
HPC, is it for high performance computing? What is the kind of job you have in your clusters?
So it's actually, it's not necessarily high-performance computing. We often call it a high-throughput computing.
High throughput.
In the sense that high-performance often means that the jobs have to communicate between themselves with something like MPI or similar.
Okay.
It's not necessarily the case. In high-energy physics, we call our use cases embarrassingly parallel in the sense that we can parallelize to a large number of concurrent jobs without them having to interact with each other.
So another characteristics, usually you say that consistency, availability, and partitioning. These three, only two of you that you can achieve. So what is the target here? You look for consistency, availability, or just the partitioning of federation? What is the key in this?
I'm not sure that this applies here. Like in this sense, it's really just a batch cluster that deploys jobs in parallel and analyzing different chunks of data. So there's really no interaction between themselves. So
let's put it: if a job dies, you don't care.
We just rerun the same workload.
So basically, you don't care if a job dies. At the end of it, you are aggregating. Correct?
Exactly. So this job's role is to run some data analysis on a specific set of data, or data sets. If it fails, we just rerun it elsewhere in the same place, and that's okay.
So why I ask this is, for edge computing, can we apply this? Is this model which you have described, do you think this will be applicable to edge computing where we have got thousands of edges and 100,000 edges?
I'm really not experienced with edge computing.
Okay, but, maybe I'll talk offline. But
yeah, I'm happy to.
This is very interesting.
Okay.
And I would like to pursue on that.
Yeah,
Thank you.
Yeah, here I have just two questions. First, which is the biggest scale this tested? Means how many physical machine?
So for individual clusters, we've tested up to 1,000 nodes. That's the biggest cluster we've had, 1,000 individual nodes. So we did a large-scale analysis before we opened the service to production for our users. We tested with small clusters, 2, 4, 8 nodes, and then 64, 128. What we've seen is that for smallish clusters up to like 128 nodes, we can easily get consistent results, like something like 5-6 minutes to deploy them. From then on, we saw some kind of linear scale with something like 23 minutes to deploy a 1,000-node cluster, which is still okay. Like if you really need a 1,000-node cluster, you can go for a coffee and come back. And then in terms of workloads running in the clusters, we've done this test the last time with the old version of Kubernetes, so we are about to redo it with 110, which is the most recent one. But we could have consistently 7 million requests per second running on one cluster, so with a sample website.
Have you figured out the bottleneck about this performance?
Right. So we are considering this for some of our experiments for managing the detectors or the analysis at the beginning, these filters that I mentioned in the detectors. So we did some large-scale tests last summer with them. The main bottleneck we had at the time was the default configurations in the master nodes of Kubernetes, which limit quite a lot the number of requests you can do. So we tuned those. I think we published at the time in our blog post the configurations that we did to the Kubernetes master to allow many more concurrent requests to the same master. And also, if you have a big cluster, you need big masters. That's also another lesson. You can't run a small VM.
I have another question. It's about the identity federation, because we use OpenStack and Kubernetes. Just want to know, you do the identity federation means the same users, same roles, or same permissions for both, or there are two?
Like for both of these use cases, the identity that we use is not like for the end application. The identity that we use is not based on OpenStack.
Okay.
So the application itself has its own way of authenticating the requests. So this is not like each cluster has its own independent way of trusting the clients. So this kubefed, one of the roles it does is that it creates an additional control plane for federation that has its own DNS. So it actually runs a core DNS, a specific core DNS, and it also has a specific set of credentials. And then every time you add a new cluster to the federation, it will also load a couple of credentials so that you can talk to the.
Well, I mean, because from my side, I think that the tenant in OpenStack and the cluster in Kubernetes can be equal between these. And at this case, can we use the same? No.
Yeah, so there's a lot of work going on the SIG OpenStack in Kubernetes to do the integration of Keystone as an RBAC backend for Kubernetes.
Okay.
So there's Dims here in the summit. He's probably the best person to talk about this. But you will be able to use Keystone as an RBAC plugin for Kubernetes.
Okay, thank you.
Okay, I think we don't have more time. No, okay, sorry, we can take it offline. Thank you.